Hello everyone. I think it's just time to start now. So today I'm going to talk about classical molecular dynamic simulations. So how are we going to work? I will first part I will talk about theory and some examples. Then we will take a break of 5 minutes or 10 minutes to answer some of your questions if there are any. And then I will switch to the second part where I present LAMMPS. So before starting, I will just say a word about me. Who am I? So my name is Ali Kerashi. I work for Westgrid and Compute Canada. What we do usually, we provide support for users for Westgrid and Compute Canada users all over Canada. And some of them are outside the country. So within the new structure of Compute Canada, there are many teams. Each team have some responsibilities. Myself, I'm a member of 2 or 3 teams. So one of the teams is called BST, Biomolecular Simulation Team. So the members of this team have at least some expertise in 1 or 2 MD codes. Usually we install those codes, we try to do some benchmarking, and we help some users to set their simulations. Second group is RSNT, Research Support National Team. This group work mainly on documentation, all the documentation you can find on Compute Canada Wiki. The members of this group write all this documentation, and this group also maintain and install software on new systems. The new installation is different from the legacy systems. What we do here, we install all the software on a different file system called, which is a CVMFS, CERN Virtual Machine File System. So we install the software once, and it will be visible for all the systems at the same time. So we don't have to go to CIDR and install one software and install the same software somewhere on Gra. So we have just to install it once, and it will be visible for everyone. And it will be also visible for the new system when they come online. Before joining Westgrid, I did some work on simulations. So I developed some Monte Carlo codes and molecular dynamics. In the next slides, I will present some examples from my previous simulation using the code I developed using Fortran to study solid liquid interfaces in aluminum nickel. I studied different materials using MD simulation, like metals and glasses, mostly glasses. So I studied silica, amorphous silicon, nuclear glasses used to confine the nuclear waste. I was interested in many properties like mass transport, solid liquid interfaces, mechanical deformation, and so on. So for this webinar, there will be 2 parts. The first one is called Introduction, where I will introduce some basic concepts of molecular dynamic simulation and give some examples from my previous work. In the second part, I will talk mainly about LAMMPS. So I will show you what can you do with using LAMMPS, how to build LAMMPS, and how to run LAMMPS. So first question, why do we need to run simulations? So if you look at all the scientific problems, except some simple cases, there was no analytical solution for every problem. So in this case, you need to do some numerical simulations. For example, if you end up with an equation that doesn't have analytical solution, you have to integrate this equation, and you have to use some numerical tools. So in most cases, the experiments are very difficult or impossible to perform depending on the conditions. Some of the simulations are too dangerous to set. And another factor is all the experiments are very expensive. So if you want to do some experiment, you have to know exactly what to do. So before knowing what to do in experiment, you can just do some simulation, and so in this case, you can know what parameters you want to do in experiment. For all the experiments are bland. You cannot control. There are many parameters, so you cannot control. However, if you use simulation, you can just, for example, fix 3 or 4 parameters and just change one parameter. In this way, you can see the effect of this parameter. So simulations can be used as a powerful tool. It can be replace experiment. It can provoke experiment. You do some simulation and you find some results. So starting from simulation results, you can start to perform some experiment to verify what you have just found. It helps also to explain and understand the experimental result. So we can just say that simulation can complete the theory and the experiment. So what kind of simulation we have? I'm interested in just atomistic and molecular simulation. So simulations that are performed at atomic level. So simulation are a tool that get insight about the properties of materials at atomic and or molecular level. They are used to predict or verify some experiment. Sometimes you have to run simulation and define some parameters. From those parameters, you can use them in another time and length scale. Using simulation, we can provide a numerical solution when analytical ones are impossible or difficult to find. We use simulation to resolve the behavior of nature of physical world surrounding us on different time and length scale. It means that depending on what kind of simulation you run, you have access to properties at different time and length scales. The applications of simulation are very wide. They are applied in physics, applied physics, chemistry, materials, and engineering, and so on. So in this slide, I will show you there are different kinds of simulation. For example, if you are running quantum mechanics, so you have access for a very short time in the order of femtoseconds. For this simulation, they are time expensive, so you cannot use more than 100 atoms or so on. So if you want to increase the number of atoms more than 400 or 1000, you have to go to molecular dynamics simulations. So molecular dynamics simulations are based on, we'll see later, that are based on force field and some parameters. In MD simulation, we use some parameters that come from experiment or quantum calculation to set the force field. If you go further for large length scale, macro scale, for example, if I use phase field theory, phase field theory used some parameters that are determined used MD simulation, like for example diffusion constant. Now, in this webinar, we'll just talk about classical MD simulation. So, what do we mean by MD simulation? MD simulation is a numerical experiment. It uses Newton's equation. So we have these equations. So all you need is just compute the forces. If you have the forces, you have already the mass, you can compute acceleration. Once you have the acceleration, you can go back to velocity. From the velocity, you go to the position. If you do this many times, so you can just have a picture of your system as a function of time. So to solve this equation, we use some algorithm to integrate the equation of motion. And this simulation are applied to systems with many particles. For example, molecules or atoms, like in metals or something. For this, we need the force field. From the force field, we can derive the forces. How an MD code works. So this is in this diagram. You will see that the structure of an MD program is very simple. So you have the first step is the initialization. So in this step, you have to set up all the parameters for the simulation, like your configuration with the positions, the mass of atoms, charges if there are, and so on. Initial velocities. The second part, which is in the middle, this is the main code of MT. So you start by computing the new forces. Once you have the forces, you use an algorithm to solve the equation of motion. Means that from forces you compute acceleration, and from the acceleration you compute the velocity, and from the velocity you have the positions. In meantime, from time to time, for example, if you run 100 steps or 200 steps or something, you want to sample. So there are some algorithms to control, for example, temperature, pressure, and so on. This is called this step sample. Then you can increase the time and do the same thing, and you can repeat this loop as necessary. Once you reach the final time you want to simulate, I can just say about the number of steps. So, for example, I can do simulation for 1 million steps, then I stop the simulation. So the forces. So to compute the forces, we need the force field or the potential function. The potential function has many terms: bonded interaction, non-bonded, and external. We can also add external function interactions. You need to evaluate the forces acting on each particle. So, for example, if you have a system of 4,000 particles, you have to compute the forces that act on each particle. Then you can just solve this equation of motion using the algorithm. I will talk about that later. So here is, for example, an example of a force field. So don't pay attention to these equations, very long. So I would just say that there are different kinds of interaction. For example, the first term is Lennard-Jones interaction. There are electrostatic interaction, and so on. So depending on the system and how complex your system, you may use one or two or more than this. So for most of model systems use the first term, which is Lennard-Jones. It works well for some systems, but if you want to change the system, for example, if you want to simulate, let's say, for example, metals, the metals you have to take into account the electronic density. For this, there is another potential called embedded atom method. If you are simulating, for example, molecules, so the angle between atoms is very important, so there are some potential that handles this. So depending on how complex your system, you will end up with one or more than one term for this potential. So now how to integrate the equation of motion. So this is a basic exercise from high school, so just it's Taylor's expansion. So if you do this expansion, then you can add the two equations, or you will end up by the position, for example, at time t plus delta t as a function of the velocity at time t. So from here, for example, if you have already the velocity at time t, so when you increase time, you can compute the position at time t plus delta t, because you know already the position in previous time. You know already the velocity. There was another algorithm which is similar to the first one. Is called Verlet algorithm. So from how it works, you have already the potential function. You derive the force. When you have the force, you have the mass. You can have the acceleration. From the acceleration, you can use the previous equation. You can have the velocity. Once you have the velocity, use other equations that gives you the position and so on. Then you increase time and you do the same. So in most MD simulations, most of the time is spent in this in computing the interactions and integrating the equation of motions. Another algorithm which is similar to this one is called leapfrog. So the first one uses the velocities at time t and t plus delta t. This one computes using the velocities at half path between the first position and the next position. Another algorithm to integrate the equation of motions is called the predictor-corrector algorithm. There are two things here. Predictor. We predict first the coordinate and we add the correction. So from the initial position velocities, we can have the acceleration. So then we have the acceleration. We can predict the position. Then we apply some correction using this formula. Now, how to set an MD simulation? So for any MD simulation, you need to set a few things before starting to run. For instance, for example, you need atomic positions. Even if you are using quantum calculation, you have always to set some configuration. So the positions of atoms. Here, for example, you have atomic positions. You have to set also the density. Your density should be real density. You cannot just take position in any order and start the simulation. You have to set the mass, charge, and so on. You have also to set, because the algorithm uses initial positions and needs also initial velocities to start the simulation. So for the initial velocities, you can say that you have already you are going to run the simulation at a given temperature. So from the temperature, you can just generate a set of velocities for each particle. There was another parameter to take into account. It is called the periodic boundary conditions. We are going to do simulation in a very small system, for example, 4,000 particles, but the properties we compute are extrapolated to bulk, so large bulk system. So we call this periodic boundary condition, which means that you take your simulation box and make some images of this box in different directions. We need also to set the appropriate potential. Depending on the system, you have to you will choose one kind of system. For model system, most of people use linear joints. For example, if you go to metals, you have to use embedded atom potential. If you are going to simulate, for example, glasses or something, you have, for example, for silica, you can use Tersov, Stillinger-Weber, and so on. There are many. Just for a more complex system, there are many potentials. For example, if I'm interested in simulation of silica, there are more than 22 different potentials. So before starting using any potential, you need to do some homework. You have to read some papers and see which potential is good for some properties and which isn't good for other properties. You have also to choose the time step. We are going to integrate the equation of motion at atomic level. So the time step should not be very large. It should be in the order of 1 femtosecond, 1 or 2. You need also to set how to control the temperature and pressure. For example, there are many ensembles: NVT, NPT, NVE. NVT means that you are running a simulation at constant number of particles, which is N, at a constant volume V, and a constant temperature. P means pressure. So this is the explanation about periodic boundary conditions. So you have the yellow, in the middle, this is your simulation box. So you replicate the same box in each direction. In the way, for example, if there was an atom that goes after this, it will be replicated in the other image. Periodic boundary conditions allow us also to have right interaction, because if you take, for example, the particle that is at the border, in order to compute the interaction that act on this particle, you have to consider all the surrounding particles. But for example, if you don't have this image in this direction, so it means that there is no particle. But with this image, you have the same environment as the particle is inside of the box. In some simulation, sometimes you have to change the boundary. For example, if you want to study shear deformation, so you have your system, so you have just to apply force in one part and apply the shear deformation. So in this case, you have to use fixed boundary condition in this direction, or what we call walls. So one of the walls will be fixed, and the other will move with a certain velocity, and from this you can study shear deformations. So neighbor list. So if you, for example, if you have a system with n particles, you have to compute all the interactions acting on each particle. So it means that for one particle you have n minus 1 loops. But if you look at the interactions, if you look at the potential after a certain point, the interaction goes to 0. So we don't need to compute all these interactions. So for this, we have just to use neighbor list. So which means that for each particle, we have to define a sphere of particles that are very close to this particle, and we store it on a table. So instead of running the loop over all the particles in the system. So for each atom, we have to run the same loop just over the neighbors in the list. For example, if you have a system of 1 million particles, maybe the neighbor list for each atom will be 100 or something like that, or less, depending on the cutoff of the potential. So the neighbor list is very important in MD simulation because it reduces considerably the simulation time. The neighbor list should be updated every n steps. So depending on your system, for example, if you are running simulation on a crystal, the diffusion of atoms is very limited. The atoms cannot move far, so the neighbor list will not change with time. But if you are running for simulation in a liquid state or very high temperature, the atoms move a lot, so you need to update your neighbor list very often. So to run simulation, there are different ensembles, and each ensemble is used for specific simulation. If you run, for example, simulation in ground canonical ensemble NPT, constant pressure. So what happened here? So the shape of the simulation box changed with time in order to reduce the pressure. The second ensemble is NVT. So here we have a fixed number of particles, fixed volume. The shape of the simulation box doesn't change with time, and the temperature also is controlled. But if you want to study some properties like diffusion, for example, you should not use thermostat to control your temperature or barostat to control the pressure. For this kind of simulation, we use NBA ensemble. So to control the temperature, there are some algorithms. For example, Anderson thermostat, Nozier-Overchain. You can find the documentation about, because there are many equations for them, so I don't want to go there. To control the pressure, there are also some algorithms. For example, for temperature, how to control. So if you are running, for example, simulation at 300 Kelvin, and when you run the simulation, you can compute the temperature from the velocities. You can have kinetic energy. From kinetic energy, you can have the temperature. So when the temperature is far from the simulation temperature, you have just to rescale the velocities in order to go back to 300 Kelvin. And the rescaling is done at a certain number of steps for the simulation. So what is the goal from MD simulation? The goal from MD simulation is to sample the space of statistical mechanical ensemble. So most of the properties can be related to atomic trajectories. For example, if you want to compute structure factor, you can just compute radial distribution functions, which is computed from MD simulation, and just do Fourier transform, and you have already your structure factor that can be compared directly to experiment. It's the same also for dynamical properties. For example, diffusion coefficients that are related to viscosity, which is accessible through experiment. So what are the properties that can be computed during an MD simulation? For example, we have kinetic energy. So we know at a given time, we know all the velocity of each particle. So we have just to use this, and you can have an average of the kinetic energy. If you have the kinetic energy, you can use the second formula to have the temperature of the system. So if you need to change the temperature of the system, you have just to rescale all the velocities according to the simulation temperature. You can have also the configuration energy. You can compute the pressure and so on. So this is an example of structural properties. For example, this is aluminum nickel system. We have here two snapshots of the aluminum nickel system. In one part we have 3 radial distribution function, and the second plot is the structure factor, where we see there is a comparison between simulation and the experiment. So for the dynamical properties, we can compute the mean square displacement. In this plot, there was a mean square displacement for different temperatures. So the mean square displacement, which means how when you during an MD simulation, all the atom moves. You have to compute the displacement of each atom. Then we sum everything all together, and we'll have a plot like this. There are different parts in this plot. The first part, the short part, is related to ballistic regime, which means that the atom moves in that when just the atoms start to move. But after some time, if the temperature is high enough, we see that the mean square displacement increases, which means that the atom moves. And depending on the temperature, you will have different mean square displacement. From this plot, you can use Einstein relations to have the diffusion constant. Once you have the diffusion constant, you can compare them to using experiment. You have access to viscosity, and there was a relation between viscosity and diffusion constant. So to run MD simulation, there are many codes. There are some open source codes, so which means that you don't have to pay anything to use them. You have just to go to the website, download the code, and compile it and use it. For some other codes, you have to pay. For example, this Amber. So you can also use your own codes. You can just develop some codes. For MD simulation, if you are running MD simulation, sometimes you need to see the structure, how it changes with time. You need some tools for visualization. There is, for example, VMD. For example, you see how this molecule change. So this is just to run MD simulation or to visualize. But when you run an MD simulation, you have also to analyze the data. So in some packages, there are some tools, but most of the time you have to develop some codes depending on what you want to do with your simulations. So now I will give some examples from previous work. So I will talk about binary metallic systems. I will talk a little bit about melting, crystallization, solid-liquid interface, and how to study crystal growth in binary metallic systems. Second part will be about glasses, how to prepare glass using MD simulation. So solid-liquid interface. So if you study, for example, metals with one component, it's easy to study the melting, crystallization, and so on, because you just start from crystal, increase temperature, then at high temperature you will obtain the liquid, and then when you quench the system, you can go back to crystal. But in case of binary systems, when you go back to, when you want to go back to crystal, it's not possible. When you cross the melting temperature, the system freezes and you obtain glass. So for this kind of system, it's difficult to study the crystallization. So for this, we have investigated how to study the crystallization in this case, and the solution is to use a system with two phases, solid and liquid. So you have to put together one part of this simulation box in liquid state and another part in solid state, then start the simulation. So for this system, aluminum nickel, we use embedded atom potential. So we have used the Verlet algorithm with a time step in the order of 1 femtosecond. We used simulations at constant pressure and using periodic boundary condition in all the direction. Using pure systems, solid and liquid, you can have access to some parameters, for example, lattice parameters, how the density changes as a function of temperature. You can have access to structural quantities like radial distribution function and dynamical quantities like self-diffusion. Now, if we use a system with two phases, we have a crystal in the middle and surrounded by the liquid. From this, so we have a solid-liquid interface. If we use this simulation, we can have access to melting temperature. We can have also access to solid-liquid interface velocity. So this are just some parameters used for the simulation. This is how the potential looks like. It takes into account the electronic density. Now these are the results. For example, this is for pure system. So there is no. For example, if you look at this plot, each point corresponds to one simulation. So for you run simulation at constant pressure starting from low temperature, you have your simulation, then you average all the properties. For example, here I have the enthalpy. So then you take the last configuration from the first simulation, then change a little bit temperature, increase the temperature, then run the same simulation for a certain time, then average the properties, and so go like this until a high temperature where you get liquid. Now, if you go back, you see that the black curve doesn't reach the red one, because in this case we cannot go to crystal using if we start from the melt, because this system has two atoms and crystal growth is controlled by the diffusion. Now, to study the crystallization, we have used the system with two phases. So that's what we have in this slide. So you have your system, which is a crystal in the middle, surrounded by the liquid. To obtain such system, we start from an elongated simulation box in one direction. So what we do, using MD simulation, we can freeze the atoms in the middle, then run simulation at high temperature to melt the two parts. After that, we quench the system to low temperature. From that system, we can start the simulation. Now it depends, depending on which temperature you start the simulation, the whole system can melt or can crystallize. From this plot, we have the enthalpy as a function of time for different temperatures. We see that sometimes we have the enthalpy that decreases, and sometimes it increases. And from this plot, we can determine the interface velocity. Once we have the interface velocity, which is presented in this second plot, from this we can determine the melting temperature, which corresponds to when the velocity is equal to 0. To characterize the solid-liquid interface, there are many parameters. For example, here I used the particle density. So what I did here, so I take the whole simulation box and divide it in different bins, then compute the density, which is the number of particles here, then represent the plot as a function of the distance. You can also use an order parameter. For example, here there is an order parameter which uses from one atom. You have the surrounding atom. You compute the angle between atoms. If you use before using this, I determined the distribution of this order parameters in a solid phase and a liquid phase. They are very separated. So it's possible to use them to distinguish between the particles that belong to liquid phase and the particles that belong to solid phase. So what happens if I run the simulation, for example, using this system with 2 phases? Here I'm running the simulation at 1600 Kelvin. So I started for a system which has a crystal in the middle, surrounded by the liquid. If I run the simulation, I will see that the system will melt completely. So after some time, the system will become liquid. And in this plot, I just represented the particle density as a function of time. So I started with a system that has already some crystal in the middle. After some time, the crystals start to become narrow. And at the end of the simulation, I have a flat line which corresponds to the liquid density. Now if I do the same, but this time at 1518 Kelvin, which is the melting point determined from the previous plot. So here, no matter how much I run the simulation, I have always the same structure. So I have a crystal in the middle and surrounded by the liquid. So all we can see here is just the fluctuation of the interface. So the particles at the interface between solid liquids, sometimes they belong to the crystal, sometimes they belong to the liquid. So they're just small fluctuations. Now if I run the same simulation at very low temperature, so I start with a system that have 1/3 in the middle as crystals. Now if I run the simulation, after some time, I will see that the middle part increases, so the system crystallizes. So the only way to study the crystallization in such systems is to use this system where we have already a solid and liquid interface. Now, how to analyze all this data? So you have already seen this plot, which gives interface velocity as a function of the temperature. So in the middle, when the velocity is equal to 0, the temperature corresponding to this is the melting point. So the melting temperature for this is about 20% different from the experiment, which can be explained by the potential. Now there was something here. For example, there was maximum. Why there is a maximum in this velocity? So, for example, now if we take this data and divide all this data by the average diffusion coefficient for aluminum nickel, we see that the maximum disappears, which means that this maximum is related to the diffusion. Now, in order to go further and study the effect of the diffusion, I will show you just this short movie. You see here there is a particle tagged here, which is almost red. So when I start the simulation, you see that this particle moves and it goes until to the crystal. So it moves all from the liquid phase to the crystal. So this means that the diffusion is very important, has a very important role in crystallization. So to go from melt or liquid to crystal, we have to move the particles and put them in the right place. For example, what makes the crystallization in binary systems more slow, because you have first to move the particles, and you have to also to find the right place, because the structure is different. But if we have only one component, so the second condition will not be applied. Now in this plot, I just reported the previous result. So I have the particle density as a function of the distance from the middle of the system. I just added, so I computed the diffusion constant, but in this time I didn't consider the whole simulation box. So what I did is I just divided the simulation box into different bins and compute the diffusion constant for the particles that are in this bin. You see in red point and this square, red squares, these are the diffusion for aluminum and nickel. We see that in the liquid phase we have almost constant diffusion, which is the same as the bulk properties. But when we go closer to the interface, there is a slowing down of the diffusion, which means that when we cross the interface, the diffusion of particles is very slow, which gives us a very slow crystallization in these systems. So to explain the crystallization, there was an old theory, which is Wilson-Frankel theory, that is based on the effect that the crystallization can be just explained by the diffusion in the liquid phase. But based on this result, it seems that this theory failed to explain some the crystallization in these systems, because it doesn't take into account the slowing down of the diffusion when we cross the interface. So these results are compared to some experimental results. In this plot, we have the red points, which are some experimental results. There are the results from the simulation, which are this black point, and the blue points came from microgravity. We see that there was a difference between the experimental and the simulation result. This gap came from the convection when you do the experiment to compute the diffusion. But now, if we compare the result from microgravity, what they do here, so they use plane, they use parabola flight. In I think 22 seconds, they simulate the gravity almost zero. During this time, they do the experiment to determine the interface velocity and diffusion constant and so on. So if you compare the result from microgravity and the result from the simulation, there is a good agreement. So now I will just talk a little bit about glasses. So to prepare glass using MD simulation, we use almost the same method as an experiment. Experimentally, to prepare glass, you have to put all together the chemical component that are required to prepare that glass. You mix everything, you put everything at high temperature, then you quench quickly the system. So using MD simulation, we do the same. We start from random configuration. You have to generate a random configuration with n atoms. Then equilibrate the system at very high temperature. Here I put 5,000 Kelvin, which it can be more than, it depends on the system. So you equilibrate your system at high temperature to make sure that you have a liquid. Then you change the temperature a little bit and run the simulation and so on until you reach room temperature at 300 Kelvin. When you reach this temperature, you need first to equilibrate the system at constant pressure to get the right density. After that, you can run NVA simulation to study the structure of the glass and so on. Here I will show you just a movie about glass indentation. So for example, you have this this corresponds to a glass with 3 oxides. So what we have here, so at the bottom there is a fixed wall. The atoms at the bottom are fixed. The atoms in the middle are free to move, and we have an indenter at the top. So I will start the movie. It will give like this. So from here you can study how the effect of the indentation on the glass. So here's just to acknowledge some people I worked with previously from Germany, from Quebec, from France, and so on. We can just take 3, 4, 5 minutes if there are any questions before switching to the next part. Yeah, we are on time. We can take 5 minutes. If you have any question, you can just post the question or. Yeah, I see there was a question about diffusion. Yes, diffusion is depends on temperature. So in some systems, for example, if you run a simulation and for some systems it's very easy to find the diffusion, but if you take, for example, the glass close to the glass temperature, I did some simulation during 8 months. I couldn't even determine the diffusion constant for this system. So it depends. But very high temperature, it's easy. So you can just run the simulation, and you have this linear regimes from that you can determine the diffusion constant. So in the meantime, if you have questions, you can just post them, and I will try to answer them at the end, or I can follow up later. For the second part of this talk, I will just go through one of MD codes, which is LAMMPS. So I will talk about LAMMPS, what can you do with LAMMPS, how to build LAMMP, how to run, and the most important is how to run some benchmarks and the performance test. So LAMMPS, what is LAMMPS? LAMMPS is an acronym of large-scale atomic molecular massively parallel simulator. So it's a code that is written in C++. It uses MPI, OpenMP. It supports also GPU. So to start with LAMMPS, you don't need to have prior. If you are not familiar with the code, it's not a problem. You can just go to the website and find all the documentation and start from there. So the first thing to do, so just go to the software page, and there are many links. For example, what I recommend for people who want to use LAMMPS in their project, go to the, for example, there is link to papers. All the papers published using LAMMPS are cited there. There is a link to each paper. At the end of each year, they put all the papers that cited LAMMPS. So by reading some papers, you can see what people have already done using LAMMPS. There are also some pictures.
Oh, we can't see the slides anymore.
Sorry. I have to disconnect and connect back. How about now? Can you see the slides now?
Yes, I can. Sorry, I have to turn off mute.
Okay, thanks. So to start with LAMMPS, you have to go to the website. There are many links. I've just said that there is a link to all the papers published using LAMMPS. There are some pictures. You see some pictures about some systems. There are also movies. So there is documentation on how to use LAMMPS and all the commands. And the most important thing, if you are going to use LAMMPS in your project, there is a mailing list. So if you have questions about LAMMPS, you can ask them there. And sometimes you have just to go there and find some people already ask that question. So you can find answers to your questions there. So this is some use cases of LAMMPS. LAMMPS can be used in biophysics, for example, for proteins. You can use it for granular flow. It can be used in material science, solid mechanics, and chemistry. There are many cases of use, so I cannot cite everything here. So if you go to the LAMMPS web page, there is a table at the beginning. So from this table, you have access to almost everything. You have access a link to download the code, manual. There is a link for pictures, publication, and so on. Just below this table, there is something. There is this recent LAMMPS news. What they put here, whenever they add something to LAMMPS, they put it here. So it's first thing to do. Now, how LAMMPS is designed. So LAMMPS is, to use LAMMPS, you don't need to pay or something. It's distributed through public license. So you are free to use it, to distribute it, and to modify it. If you do so, if you modify something, for example, if you add a potential or a package or something, you can also contact the developers. They can add it to next version of LAMMPS. LAMMPS is the first version of LAMMPS was written in Fortran. Then they switched to C++. It uses object-oriented approach. It has different parallelization using MPI, OpenMP, and GPU accelerator. LAMMPS is invoked by commands. There are some packages you have to use the interface to run the code, but for LAMMPS you need just to compile the code. You have the binary. You need to have a script, which is a text file, the input, and run the code. So, which is very suitable for high-performance computing. Using LAMMP also you have the possibility to customize the output. When you run a simulation, for example, if you want to have to print just the pressure, you can just print the pressure. If you want to print something else, there is a way for that. And the most important thing is LAMMPS can be compiled as a library. Once you have the library, you can call the library from other codes. For example, if you are developing a code and you need to compute, for example, the potential, so you don't have to implement that potential in your code. Just compile LAMMPS as if LAMMPS has that potential, just compile LAMMPS as a library and call it from your code. Now, how to obtain LAMMPS? To obtain LAMMPS, you have just to go to the website and download the code. So there are different methods to download the code. So you can download the Windows installer. So there is a binary to install under Windows, which is good just for testing or for developing your input script. You can also install it on Mac, which is also good for testing because you cannot run a longer simulation using your laptop or something. It's also possible to download the RPMs, but the problem with RPMs, you cannot install them because if you work, for example, on any system, you don't have access to root to administrator, and the administrator will not give you access to install that. So the best way to work with LAMMPS, you have to download the source file, source code, then compile it. Now, how to build LAMMPS? So as I told earlier in the previous slide, so it's possible to build LAMMPS from RPMs. It's also possible to run it on Windows just for testing, not for production runs, because you cannot run large simulation on your laptop. And the best thing is just to use the source code, download the code, compile it, and if you do so, it's possible to keep track of the old version. For example, I can install the previous version. If a new version is online, I can just install it and have both versions, which can be used through modules. Now, this is, for example, for Windows. You can just, like every program in Windows, just click and install, follow the instruction. It will give you the binaries, and then you can run it. Now, if we want to go to build LAMMP from source, so we have to download this file. So from this page, then it will give you the last stable version, lamps-stable.tab.gz. Now, once you download, so you have to enter this function. So if you go to the directory, there are many subdirectories inside. There is, for instance, bench, which is the benchmark test. There are some tests already with output, example to see. There is also a directory for the documentation. As PDF files or HTML, you can just use them. But for the documentation, it's better to use online documentation, but because it's easy to navigate rather than look into text files. There is directory examples. In this directory, there are many different cases of use of lamps. There are, I think, more than about 300 different input files. There is another directory leap. This directory includes some libraries. So before building lamps, sometimes you have, if you know, you need to include one of the packages, you have to build first the library. I will show you later how to do that. There are also two files, README and the license. You can check what is inside. There was another subdirectory potentials, which have some examples of the potentials used in LAMMPS. And the source files are in the subdirectory source. I will go there later and show how it works. There is another subdirectory tools, which contains some tools, some programs. They are easy to compile. Just they use. There are serial codes. Just to go there and compile them. You can use them. For example, for LAMMPS, for visualization, you can use VMD. But there is another tool called Xmovie. You have to. It's in this directory tools. If you can build it and use it for visualization, but the visualization in this case is just two-dimensional. But using VMD, you have 3D dimension. So now to build lamps. So what you have to do? So first you have to build some libraries. Some libraries may be already installed in your system, but some others you have to build them first. Then you need to choose a makefile. There are already some makefiles that came with LAMMPS. So you have to choose one makefile which is suitable for your system, depending on what compilers you have, what libraries, what OpenMPI, and so on. So the first, once you have all these settings, so sometimes you need to edit the makefile and change some path for the libraries. So the first thing to do is just go to SRC and type make. It will give you some information, and from that you can continue. For example, there are different commands that came with make plus argument. If you type, for example, make package, it will list you all the packages that are included in LAMMPS. When you build LAMMPS, you can add some packages or remove some of them. It depends on what you want to do with that. In the latest version of LAMMPS, there are, I think, 60 or 62 different packages. So if you build completely LAMMPS, it will take you 1 or 2 hours just to compile it. But if you don't include all the packages, it can be compiled easily. So now to see, for example, the packages that are included, you can use this make package status. For example, if I want to add a package with a given name, just type make yes the name of the package. If I want to remove, just make no the name of the package, and so on. So for the make files, there are different. So for example, you can use MPI, serial, ICC, OpenMPI, and so on. So I will just do a short demonstration on how to build LAMMPS. So for this, I have to switch to terminal. In a second, I have to connect first. So now I'm connected to Great. So I have this this file which I download. So I have just to enter this file, tar minus xvf lamps stable. So there are many files there, so it takes a few seconds. Now it creates directory lamps-11 August. The name changes depending on the version of the program. So what I have here, if I have just tap ls, I will see all the subdirectory I talked about earlier. So what do I have to now to compile? So first I need to build some libraries if I want to include them. So to do that, I can go to this subdirectory lib. Yes, you see there are many. I will take just one easy, very quick to compile. So there, for example, this modified embedded atom potential. So it's there are some codes in Fortran. There are some make files how to build this library. So for example, here if I type module list, so I have already Intel compiler and OpenMPI available in my environment, so I can use them to compile. In some systems, there was no default modules, so if you want to compile, for example, you have to load manually a module for that. To see all the modules, just use module available to see all the modules. Then choose the module you want and type module load that module. You will have the module available in your environment. For this, for example, there are many make files, so I have to choose one. There is, for example, make file ns make file. For example, there is make file Intel Fortran. I have Intel compiler in my environment, so I can just use that. So to compile, so just type make minus f file, the name of the makefile.afort, so it will compile. So there was no problem, so I have already my library here. The library is a file with extension .a, star.a. So I have my library here. So if I want to build LAMP using this package, I have already the library, so I have just to add the package there and compile. Now I have to go to source code, where I can build LAMPS. source. So there are many files here. I have already built LAMMPS here. So first thing to do, just type make to see all this information. So there are many informations to see. It will explain you what to do if you want to, for example, make package status, all this information. So now I am in this directory. If I want to see the packages, just make package. So these are the list of the argument I can use. For example, make package status. So it will print some information. For example, if I take this one, installed no package user OMP. So it means that this package is not included yet. But if I want to include it, I have just to type make yes and add the name of the package. Now, if I want to build, I have to find makefile suitable for the system. I have Intel compiler, so I will just use makefile that have Intel. So the makefiles are located in this directory make. So there are already some makefiles. Some depending on how is configured your system and what compiler you have, it may work directly. And sometimes you have to change the makefile and set some paths and add some libraries. In this case, the makefile I want to use is located here, options. There is a makefile Intel ICC opening PI. So this is makefile ICC opening PI. Now, if I want to use this, so I have just to type make ICC underscore open MPI. So this is the argument. When you specify this argument, the GNU make will pick this makefile and start to compile. So here it says that the program is up to date because I built it already. So if I want to recompile, so I have to remove the old ones. So to remove the old ones, just type make clean dash all. So this yeah, for the if you install LAMMPS using Windows installer, you have to go to program files and you will find the directory there. So to build, I have just to type make ACC open MPI. It will start to compile. If there was no problem, at the end I will get executed. This will take a few minutes. I can go back to my slides. So this is just how to build. So you have to download, enter the file. You will see all the subdirectories. You have to choose the right make file and type make, for example, this I choose ICC underscore open MPI. For this, you need to have Intel compiler in your environment and OpenMPI. Now, how to run LAMMPS? When you compile, you will get binary or executable. If I use, for example, ICC underscore OpenMPI, at the end I will get an executable LMP underscore ICC OpenMPI. You can rename it if you want. Now to run, you need an input file where you put all the commands. You need the potential. To see the potential, you can just go to the examples. You will find many examples there. Now to run LAMMPS, you can run it interactively. You will print the output on the screen. But if you submit a job to compute nodes, you need to redirect the output files to a file. So you have to use the redirections. Now there are many commands many options when you run the LAMMPS. For example, you can use for the -L to specify the log file, -I to specify the input file, and so on. You can run it in parallel, for example. This example, I have MPI run -NP8. It means that I will ask for 8 processors to run this code and redirect the output file called my.log. So how a simulation run looks. So there are two parts. The first part is the input file. The input, there are initial positions, initial velocities, time steps, the mass, periodic boundary condition you want to use, the potential, and many other parameters. And for the simulation, there are many kinds. You have to set what ensemble you want. NPT, constant pressure, constant volume, or NVE ensemble. Using LAMMPS also you can do minimization. You have a configuration, so you can just use the minimization to minimize the forces. It's also possible to use Monte Carlo simulation using LAMMPS. There is also you can combine between atomic and continuum simulations. And from the output, you have a choice. You can have the trajectory, which is the image of the system as a function of time, which means that you have to record the position of each atom at different times. You can record the velocities, the forces, the energy as a function of time, temperature, how the temperature changes as a function of time, the pressure, the density, the simulation box length. You can also keep some images. If LAMMPS is built with JPEG and PNG libraries, there are some commands to transform the trajectory to a snapshot. You can also create some movies.
That is just 500 or 400 meters from the right on the opposite side. You are now close.
So So this is how it looks like. So you have choose to customize the output and so on. So the command lines. How it works? You have your executable at the beginning. You have the input file, and you redirect the output to a given file. So there are different parts in the script. So the first part is the initialization. You need to specify which unit you are using, the dimension of the problem, 2D or 3D, periodic boundary conditions or fixed boundary conditions, and so you have to put also the atomic positions, and there are different possibilities to get them. For example, for simple systems, if you take BCC, FCC, or something, you can just use the command from LAMMPS, and you generate the initial positions. You can also read the positions from a file. If you have already a file that have the positions, you can read it and use it in LAMMPS. But in one condition, you need to write that file in the same format that LAMMPS can read. You have also to set the velocities. The velocities can be read from a file if you have already, because when using MD simulation, it's always possible to have a checkpoint. It means that you have all the variables at one time. You can use this file to restart the simulation, continue. It can be, the velocities can be generated from lamps according to the temperature you set. So you need also to set all the potentials per style, per coefficient. For example, if you use linear Jones, you just have to put per style linear Jones with the cutoff. Per coefficient, with the coefficient, if you have, for example, two types of particles, you have the coefficient between particle A and A, the coefficient between particle A and B, and so on. Then you have to put some fixes and compute. Fixes, which is related to the ensemble, for example, fix or NVT, NPT, and so on. For example, during the simulation, you can compute some properties or the average. For example, if you don't want to have all this data, you can just compute some of them. There are some commands you can use and customize how you want the output file. At the end of the input file, there is one command. So if you type run this number of simulations, so simulation will run during those number of iteration. You can use minimization. Depends what you want from your simulation. So here is an example of the input file. If a line starts with hash sign, it means that it's a comment, it's ignored by the program. So we start by setting some parameter here. For example, we put unit, linear Jones, atomic style, atomic. So all these comments have different arguments. So all the arguments are and the comments are documented on the website. So the second part here is how to generate the simulation box, lattice, region, and so mass. So all these lines just to generate the simulation box. Now if I want a larger box, I have just to change this. Instead of 10, I can use more to have a bigger simulation box. If I have already the simulation box in a file, I can just remove all this line from lattice to create atoms and replace it by one command, which is read from this file. This command velocity all create, just to create the velocities, the initial velocities. Then there was for the potential style linear Jones. cutoff to 2.5. This is the cutoff for the potential. It means that if the distance between the particles is larger than 2.5, the interaction goes to 0, so we don't have to compute those interactions. Per coefficient, this is the coefficient. If you have seen the Lennard-Jones potential, it has two terms. There are two parameters. So these are the parameters for that. So I talked already about the neighbor list. Here it says neighbor list modified. So this means that the neighbor list will be updated every 20 steps. Now I was talking about thermodynamic ensemble. Here we use NVA. We can use also NPT or something else. There is this command damp. If you want to have the trajectory, for example, if you run a production run and you want the trajectory to process later, so you can store all the position as a function of time, and you have a choice what to store, the positions, the velocities, and so on. But it generates a lot of data. It's up to you to see how. This is a log file. It's possible to, at some point of the simulation, redirect some data to a log file inside the input or from outside, as we have seen from the redirection. Thermo, it's a command to print out thermodynamic properties like pressure, energy, potential energy, kinetic energy, and so on. So here I ask the program to print every 50 steps. If I don't specify the format, there was thermostyle. So by default, LAMMPS prints 5 or 6 different thermodynamic properties. But if you want to change this, because it depends on your simulation. For example, if you are running simulation at constant volume, you don't need to have the volume in the output because it's fixed from the beginning at the end. But if you run simulation, for example, at constant pressure, the pressure changes, the volume of the system changes. So you may want to have this in the output file. So thermostat, custom, stack, temperature, total energy, and so on. At the end, there is the command run. Here I ask the program to run 250 steps. So for initialization, there are many commands. So all these commands are documented on the website. So if you need something, you have just to go there and find what every command do. So this is for force field, per coefficient, and so on. Neighbor list, fixed NVT. Already talked about this. How to customize the output. So the output, there are some keywords. But if you want, for example, to have the pressure, just use pressure. This is potential energy, kinetic energy, total energy, and so on. Now I will just run a short test. I have to switch back to. So here, when I try to compile, it says that there was a problem. Cannot find this library. So we need to solve this problem. So for this, I have to find where this. So the problem came from here, because I wanted to add modified embedded atom potential, and here this is the name of the library is not the right one, so I have just to I think this one, if I remember correctly. And then now I will just show a demonstration. Here. So I have already here some examples just copied from this directory examples. So now if I go to this directory colloid, so I have the input file. This is the input file. So it has all the settings we talked about: unit, atom style, lattice. It will generate this system. There are has only one atom. Two type of atoms. Type 1 with mass 9 and so on. It will generate the velocities. Here will enable this. This is the coefficient for the potential, and it will run in NPT, constant pressure simulations. And for the output, it will print the step, temperature, energy, total energy, pressure, and so on. The time step is set to 0.005, and the simulation will run 5,000 steps. Now I have this script to run this system. So go local. Here I go local. So here I just set the path to the version I built now. So since I used these two modules to build the program, so I have to load them before running the job. It's the same when you submit your job to compute nodes. You have to load the module first in order to be able to use the program. This is just the path to the binary. And here I just specify the input file, the output file, and now I will run this program interactively, so I don't have to redirect to the output file. So to run it, just go. So I tried to run this, but it says something unknown colloid per style. So this means that the version I just built now didn't include this package. So I cannot run this particular example using the version I just built now. But I can run it because I have another version of LAMMPS that is built completely and includes this package. So I have to load the module. If I type module available, just type LAMMPS. So you see here there are many different versions of LAMMPS. So I will just choose one. So what I did here in this second script, module. So module purge to remove all the modules that are loaded. Then I will load this version of LAMMPS from 11 August and run the program. So just go module. So you see that it takes a few seconds. Now if I want to change, for example, go to the input file. Now, for example, I have this system. If I use 30, 30, 30, it will give me a certain number of atoms. If I want a bigger system, I can change here. Instead of 30, I can put more. But it's possible also to use replicate. For example, if this part is, I can read this part from a file, so I don't have a choice to change these parameters. But there was another command which is replicate. This will replicate the system in different directions. I will go to another example.
Ali, maybe before you go to another example, we have 2 questions in the group chat that
Yes.
might be timely to answer. There is one from Tamana, and then another one that I received through email. Ali, are you still there? Ali, can you hear me?
Oh, I see there are many questions. So, for example, the question about Windows, of course, when you ask...
If you could put your headphones and microphone back on, it'll be easier to hear you.
Yeah, I see the question. For example, the question about Windows. When you install the program with Windows, you don't have access to source, just binary. If you want to binary,
can you connect the laptop and use your microphone?
Yeah, it's not working like this. Can you hear me?
Yes, that's much better. Thank you.
Okay. So the question about Windows, when you install using Windows, you don't have access to source, just binaries. If you want the source, you have to download the source code.
Okay, that I got. Thank you.
And the other questions about generating the configuration. There are simple configurations you can generate using LAMMPS. For example, if you have an FCC if you have, for example, a FCC system for BCC or something, there you can use this command lattice, specify, for example, FCC, BCC or something, and some parameters. It will generate the file. Otherwise, for some complex system, you have to use your own code and generate it, or some other programs to build the system. It depends on your system. I think there's the other question. For the question about metal and organic, I think it's possible, but the problem is how to define the potential. If you have a potential that can give you the interaction between your two systems with metal, and I think it's possible. But I never done that. Don't right answer for that. So now I will go to the second example. So this is an example. So this is a very simple example. It's linear Jones. So what I did here, I just ran a short simulation and plot some. So if I want to run, so just run the example like this. Everything is set already. will generate some input. It is done. So, but I have already some. I want to show you the thermodynamic parameter properties as a function of time. So for this, I have already a file with plot.gnu, where I put all the commands to plot. I don't have to type everything now. Right? So to use this, I need a program. I have to use GNU plot. So I have to load the module first. Module list. So there was already a module available here, GCC and GNU plot. So I have to use GNU plot. GNU plot. Then load the fichier. Now I will show you how the temperature changes as a function of time. You see, for example, here I have the simulation at 300 Kelvin, and the temperature fluctuates around this value. And the next, this is the potential energy. This is the enthalpy of the system. This is the pressure, how the pressure changes over time. This is the volume of the system, and so on. So when you have this data as a function of time, for example, this, you have just to average all this value, and you have your, for example, your average value of the pressure or density and so on. So now I have to go back to my slides. So we have seen how to build lamps, how to run, and so now the problem comes in how to go to the output files. And so when you run lamps, it prints all the input data you have used. For example, for this system, I have used 4,000 particles and so on. I will just to tell you something that at the end of the simulation, there was this small table where it prints pair, neighbor, communications. It will gives you the time spent in each part of this program. For example, in this example, I used I think 12 cores. So the time spent in computing the pair interaction is 46%, and 44% of the time is used on communication. So, which is the efficiency of this of the program for this typical system is very low. So before running large simulation, it's better to do some benchmark and see how the efficiency of the program changes as a function of the number of cores you are using. I have some examples later here. For example, this one, for example, potential. How many of you may ask this question? For example, I do simulation using, for this system, it takes 1 day to finish the simulation, but when I change to the other system, it takes more. Yeah, that's normal, because depending on what potential you use, the simulation time is different. We have seen in previous slides that the potential have many terms. If you use, for example, just the first one, linear Jones, it may be very fast. But if you use other, it will be slow. So in this plot, for example, I have something like 24, 25 test cases I took just from the directory examples. I just ran them for a short time, 1,000 steps, and just to see the time used to compute the pair interactions. I see that for most examples, the I just used one processor for this system because if I use more than one, so I might have some time spent for communication. So I want to remove that. So just to see how much time it takes to simulate using one potential and another. I see here that most of the potentials use more than 80% of the time for computing the interactions. Now, if I take just one potential, I took here terms of potential, which is used for glasses, for silica. So I take a system with 8,000 particles and run the same simulation using different number of cores. I started from 1 until 96. I see that if for very short, for a minimum number of cores, for example, until 8, I have a good efficiency, which is between 90 and 100% of the time used by the per interaction. But if I add more CPUs, so I see that the efficiency of the system is very low, because when you increase the number of cores, you increase automatically the communication between the cores. So the time spent in this case, for example, using 996 cores, the system spent more time in communication than computing the interactions. We see the same also if we increase the number of particles to 125,000 and so on. So I did the same for different until 1 million particles. So the point from this, that before you start extensive simulation using a given system, it's better to do some benchmark, which means that you have to run a very short simulation test for 100 steps or something. Then compare the time using 1 core, 2, 3, 4, and so on, and you see you will have a better combination for your simulation to take advantage of the system, because it doesn't make sense to ask for 96 cores if you spend most of the time in communications. So why we have this time of spent in the communication? So how it works in MD, for example, if you are running on one CPU, so the one CPU will compute everything for the whole system. But now, if you increase the number of CPU, the program will divide the system in in very small subsystems according to the number of the CPU you asked for. If I asked for 16, so the whole simulation box will be divided in 16 small boxes. So if you increase the number of the small boxes, so you will increase the communication between the processors to communicate the information, because when we go to the border, for example, to compute the interaction, you need the information about the position that belongs to the box that sits next to that particle. So if you increase the number of small boxes, you increase automatically the communication. If you increase the communication, you will spend more time for nothing. Here I have an example with 1 million particles. I see that I have a good efficiency until 16 processors. But if I increase more than 16, I spend more than about 40–50% in communications. To learn more about LAMMPS, you have just to go to the website. There are some examples. before running your own simulation, you can start by running the examples that are provided. Most of the examples work, but if it happens that something doesn't work, it doesn't mean that the problem is in the script, but maybe in the version of the LAMMPS you built. If you didn't include the corresponding package, there might be some examples that will not work, but most of them work. And you need also to check all some papers that are published to see what people have already done with this program. That's what I have for today. Thank you.